Today, we're going to find some more Taylor polynomials, and then we're going to put dot, dot, dot at the end of it. And so we're going to find some more Taylor series. And then we'll see what we can do with this information. So when we're constructing a polynomial, our concern is what should, the polynomial part determines the form of the function that we're building. So we're going to construct a Taylor polynomial. So it's going to look like a polynomial. There'll be a constant, there'll be an x term, there'll be an x squared term, and all the way up to an x to the n term. So that's the form we get just from deciding that we're going to build a polynomial. We have to put the work in to find the coefficients of the polynomial. Our job is to find the coefficients of the polynomial. Remember that we're going to construct a Taylor polynomial by matching derivatives. That is, I want the ith derivative of the polynomial Tn of x at x equals a to be equal to the ith derivative of the function at x equals a. That is, the ith derivative of Tn at a should be equal to the ith derivative of the function at a for all values of I, up to the degree of the Taylor polynomial. So we're building a polynomial by matching derivatives. So all we need to do is find the function evaluated at a. That'll be the constant for our polynomial. The first derivative evaluated at a will be the coefficient of x in our polynomial. These first two terms together give us the tangent line for the function. So like we said yesterday, Taylor polynomial is just a tangent line, but keep going. Then we find the second derivative of the function evaluated at a and divide by 2 factorial. And in general, we find the nth derivative evaluated at a and divide by n factorial. So the factorials are there because we want the derivatives to be the same. And if I take the derivative of, let's say, f double prime of a over 2 factorial times x minus a squared, the first thing we do is we pull the 2 in front and we reduce by 1, and then the 2 cancels out the 2. So that when we take the next derivative, we're just looking at f double prime. Just follow that through here. If we take the first derivative of Tn of x, we bring the n down in front, it cancels the n factorial and leaves an n minus 1 factorial. And the exponent is now n minus 1. Then we take the derivative again, and we bring the n minus 1 in front, which cancels the n minus 1 in the n minus 1 factorial, leaving an n minus 2 factorial, and the exponent is now n minus 2. And so by the time we get to the nth derivative, we're just left with the constant fn at a. So it makes sense that those factorials are there. Those factorials are there to be the derivative, to cancel out, moving the exponent down into the coefficient, multiplying the coefficient by the exponent. So if we want to find the Taylor polynomial of a function, we just need to take a bunch of derivatives. So let's do that. Yesterday we did e to the x. So we found out an important one. So we know that e to the x is equal to the sum as n goes from 0 to infinity of x to the n over n factorial. That's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. That's one that we have to know. You don't have to memorize it, you just have to remember it forever and ever. Seriously, I find students 10 years on and I say, what's the Taylor polynomial, or what's the Taylor series for e to the x? And if you're employed, then I show up with your manager. I'm like, well, what's the Taylor polynomial for, or what's the Taylor series for e to the x? And if you're not, like, oh, the sum is actually n over n factorial. Then me and the manager, we let you keep your job. I'm just kidding. That doesn't happen at all.
Then who's going to make the Slurpees?
I'm just kidding. I actually do that to all my students who are employed after 10 years, but in this economy, I'm just kidding. You'll all find jobs. Which, by the way, is the horror of this show. This is what makes this a horror movie. You'll all find jobs. It's supposed to sound comforting, but think about what it means. Oh, good, we'll find employment. Oh, and all that comes with it. See, it's like one of those wishes where the genie twists your wish into a horror movie.
Yes, you get to continue. You get to continue to eat, but I'm going to take away 1/3 of your life every day.
Yes. And if you don't do this, society has deemed you deserve to die. Let's find the 5th degree Taylor polynomial approximating let's say f of x equals sine x near x equals 0. There we go. Now we got the formula at the top. So let's find the 5th degree Taylor polynomial approximating sine x near x equals 0. So this means that we need to look at the function f of x evaluated at 0 and all of its derivatives evaluated at 0, at least to the 5th derivative. We need to do this until we can find some kind of pattern that will work. So I need to take f of x. So f of x is sine x, and f of 0 is 0. Sine of 0 is equal to 0. So that's that first term. It's going to be a 0. I need to take the derivative, f prime at x. The derivative of sine is cosine x. And cosine of 0 is equal to 1. So now I got the coefficient of the x term. This makes sense. We know that the tangent line for sine x near 0 is y equals x. So everything makes sense so far. We'll take the second derivative at x. The derivative of cosine is negative sine x. And so, oops, this is f prime at 0. And so f double prime at 0 is equal to 0 again. The third derivative, the derivative of negative sine is negative cosine x. And so the third derivative evaluated at 0 is equal to negative 1. Oops, that's going off. There we go. The fourth derivative, usually we stop writing after 3 primes and we just put a 4 in parentheses. So this is a pretty standard notation. If we want to indicate the fourth derivative, rather than writing 4 little primes, we just put a 4 in parentheses. Depending on how we draw 4, this is actually, 1, 2, 3, 4, 5 little marks, but it doesn't take up space horizontally. The derivative of negative cosine, we're at the fourth derivative and we started off at sine, we're back to sine, and we're just going to go in circles now. The fifth derivative of sine is, since the fourth derivative is back to being sine, the fifth derivative is going to be the cosine. So f prime is also the fifth derivative . So now we just need to take these coefficients and drop them into Taylor's formula. In this case, a is equal to 0. So we can say that sine x, well, I said I wanted to find the 5th degree Taylor polynomial. So T5 of x will be 0 plus 1 times x minus a. In this case, since a is equal to 0, this is a polynomial that's going to be in terms of x. So this will just be an x polynomial. A polynomial in terms of x. It's not a former polynomial. It is still and always will be a polynomial. So it's just going to be 0 plus 1 times x plus f double prime at 0 divided by 2 factorial. F double prime is going to be 0. So 0 over 2 factorial x squared plus f triple prime over 3 factorial x cubed. F triple prime is -1 plus the fourth derivative at 0 over 4 factorial x to the fourth. And then the fifth degree term is back to being 1. So notice that I'm just filling in the numerators of my coefficients. The rest of it is just a form. And I'm just replacing the ith derivative at 0 with whatever the ith derivative is. And that follows a pattern: 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1. I have to hit Control C, otherwise I'm going to just go on forever. So we can see that the fifth degree polynomial, we're going to have an x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. There's our fifth degree Taylor polynomial. So T5 of x will be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. This is really cool. I got a polynomial and it only has odd powers, and sine is an odd function. So that kind of worked out pretty cool. Also, we can see what the pattern is going to be. Notice that we just needed the fifth degree terms, but if we kept going, the second derivative is also the sixth derivative because of the way these functions work. And the third derivative is also the seventh derivative because of the way these derivatives are going together. And the eighth derivative is the same as the fourth derivative. And that means that the ninth derivative will be the same as the fifth derivative. So now we can see what the pattern is. It looks like sine of x is just going to be the odd ones and alternating. So x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus x to the ninth over 9 factorial. Let's see what this looks like in a graph. And let's laugh at our instructor as he set this up previously and then promptly closed his graphing calculator browser. So let's hit the old share screen. Take a look at my graphing calculator here. So the first one that we had, the first degree Taylor polynomial, is just y equals x. There's the tangent line. If we start adding terms to this, the polynomial will start to look more like sine x. So the second degree term is 0. That doesn't help us. But the third degree term is minus x cubed over 3 factorial. And so notice now we're starting to see those two bumps. That first one after the origin and the first one before it. And then the more terms we add, the more our polynomial starts to look like sine, near 0. If we try to look at this far away, then it stops looking correct. But if we just keep using more terms, we just keep expanding this range where this polynomial looks like sine. Any questions? Sine is the odd one. I said you also need to know the Taylor series for cosine. And we have a bit of an advantage here. Turn off these, but keep them visible. We notice that the cosine is the derivative of the sine. So I'm just going to take the derivative of my Taylor polynomial. So the derivative of x is 1. There's the 0th degree Taylor polynomial approximation. The next term will be the derivative of x cubed over 3 factorial. So the derivative of x cubed is 3x squared, and then 3 will cancel out with the 3 from the 3 factorial and give us minus x squared over 2 factorial. And we start to build a polynomial that's trying to look like cosine. Then I'll have a minus x to the 5th. And on a plus x to the 7th. Minus, plus, minus, plus, minus. Yeah, there, that's better. I'd say, how do you guys let me get away with that? But, you know, I can't see the chat right now, and I think the volume is low on my computer, so you could have been screaming at me. It's like, oh, there's a minus in the wrong place. You made a sign error. Oh, well. So if we just start taking derivatives, here's cosine. Here's the tangent quadratic. We don't really have tangent quadratic. That's gets the idea across, but it's not the thing that we're actually going to call it. Then let's take the derivative of the next term, which is plus. The derivative of x to the 5th is 5x to the 4th. And then the 5 will cancel out the 5 factorial and leave a 4 factorial. So the next term is an x to the 4th over 4 factorial. And just like before, the more terms we add, the more the polynomial looks like cosine. And this is even extra cool because sine is an odd function. Its Taylor polynomial is all the odd powers. Cosine, being an even function, has all the even powers. This is just really good design. I like it. Any questions? Then you put them all together and it just looks like a mess. So this is the other reason that Desmos is a better graphing calculator than your graphing calculator, like your TI-84, at least for graphing. Which is weird because this will always be referred to as a graphing calculator, even though it's kind of not very good at graphing anymore. This was really good at graphing back in the 90s. But remember in the 90s, we were like playing Game Boy and stuff like that. And we're like, oh, wow, look at this. We want a little bit better graphics now, which is strange that Among Us was so popular because the graphics are kind of like just, it's low res. And Minecraft, of course, you could see all the little pixels and stuff. One of my favorite Star Wars properties of all time is the game Knights of the Old Republic, which came out in, I don't know, 1884 or whatever. And I thought, oh, I should get that again because that was, I've always said, one of the best they could make a better Star Wars prequel just by filming someone playing that game through. And then you can make a bunch of them just by playing the same game over and over again because it's a better story than almost anything that we have in a Star Wars film. But anyway, I digress. I started playing it and I kind of had to stop because the graphics were very dated. And I go, this looks kind of bad. And I kept getting distracted by it. Which seems strange because we're always like, oh, it's the story that matters. Like, oh, nah, it is kind of a little bit how it looks. I think I'd be able to, but I had just been playing like Red Dead Redemption 2. And then I think it was too shocking to switch back. I should get out my old Atari 2600, play combat for a while so that when I start playing Knights of the Old Republic, it looks awesome again. So maybe I should do that. So what we have, we're trying to build a list of Taylor series that we recognize. So we've got e to the x is the series as n goes from 0 to infinity, x to the n over n factorial. That's going to be 1 plus x squared over 2 factorial, x cubed over 3 factorial, and so on. This n factorial in the denominator suggests that the interval of convergence for this power series is all real numbers, which it is. We could run a ratio test to do that, but it's better to just look at this and say, we know what's going to happen if we do a ratio test. We found a new one. We found sine x is the odd one. It's the sum as n goes from, I'm going to start the counting at 1 because we could start it at 0. That would be just fine. But let's start the counting at 1. And let's make sure we get all the elements. It was alternating. So I need a minus 1 to the n. And it started off positive. So I'm going to call it n plus 1. Then we had all odd powers starting with 1. So I'm counting n by integers. So I'm going to make my exponent 2n minus 1. So 2 times 1 is 2, 2 minus 1 is 1, 2 times 2 is 4, 4 minus 1 is 3. So, and there's still that factorial in the denominator. Just need to remember sine x is the odd one. So sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. This is a power series. I've gone from polynomial to series by putting dot, dot, dot at the end. So now we're concerned with the interval of convergence. If we look at the interval of convergence, we see a factorial in the denominator with no factorial to fight it in the numerator. So we should guess that the interval of convergence is all real numbers, and our guess would be correct. And we also found the Taylor series for cosine. So cosine x, we could find the Taylor series for cosine x by taking derivatives, or sorry, by taking derivatives of cosine, plugging in 0, doing all that. But we can also notice that cosine is the derivative of sine, and just take the derivative of what we're looking at here. Cosine still alternates, and it starts off positive as well. So it starts off with a positive 1. Just take the derivative of this term, and we'll get x to the 2n over 2n factorial. So we'll have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. E to the x has all of them. Sine is the odd one, cosine is the even one. E to the x doesn't alternate, sine and cosine do. Any questions? We need to build a repertoire of power series that we just recognize, so that when they show up, we can say, oh, this is just e to the x. I've already implied something that we can do, because I said, let's find the power series for the Taylor series for cosine x by just taking the derivative of sine of x. And that seemed to work. What you should do is not trust me and say, hang on a minute, I'm not sure that that's the case. What if I'm just going to set up f of x as cosine x, take a bunch of derivatives, and plug in 0? And what you're going to find is that the even ones will come up with 1 or negative 1, and the odd ones, which will be sines, will come up with 0. So it'll work out. Trust me. I'm just kidding. Don't trust me. Verify this. This is verifiable. Notice that if we take the derivative of e to the x, the derivative of 1 is 0, but the derivative of x is 1. The derivative of x squared over 2 factorial is x. The derivative of x cubed over 3 factorial is x squared over 2 factorial, and so on. So the derivative of the term is the previous one. So if we take the derivative of e to the x, we get e to the x. So apparently, that's a thing that you can do. So we're in the process of building our repertoire of recognizable Taylor series. Let's take a look at another one. Let's let f of x be sine of x squared. Right now, you may be thinking, I hope we can do this the easy way. So depending on what happens when you first look at what I've just asked you to do here, I haven't asked you anything, I guess. Find the Taylor series, find the first 4 non-zero terms of the Taylor series approximating f of x equals sine of x squared near x equals 0. Here are the 3 things that we might notice. First, we might just start taking derivatives. Like, oh, well, we know this process. We've got a new function. We'll take a bunch of derivatives. We'll plug in 0. Everything's fine. Then some of you have thought about that step and said, that's fine. We'll just take a bunch of derivatives, plug in, oh no, this is going to be awful. Some of you see that right away. It depends on how automatic your differentiation skills are. Some of you see how much of a hassle it's going to be to take a bunch of derivatives of this function. And you're starting to think about, how can I get around this? I don't want to take those derivatives. Leach always tells us the point of being in a math class is to learn enough math so that we don't have to do all that math. That's the point. So some of you might be thinking, can we just plug x squared into the Taylor series for sine x? And you're like hoping against hope. For those of you who don't see why that's our concern, let's start taking some derivatives. So f prime at x, the derivative of sine of something is the cosine of that thing times the derivative of that thing. No problem. We need to plug in 0, so I'm going to say f of 0 is sine of 0 squared, which is 0. Yeah, that seems pretty cool. That's no problem. F prime of 0 is going to be the cosine of 0 squared times 2 times 0. So that's 0. That's fine. First derivative is still 0. We haven't got a non-zero term yet. And I said to find 4 non-zero terms. No problem. Let's just take some more derivatives. And now we should start seeing why this problem is not going to be fun. Because to take the derivative of cosine x squared times 2x, we have to use the product rule. The derivative of the first times the second plus the first times the derivative of the second, or however you like to do the product rule. The derivative of cosine of x squared is minus sine of x squared times 2x times the second, which is another 2x, plus the first, cosine x squared, times the derivative of the second, which is just 2. No problem, you say. We can simplify this. Let's see. I've got a minus 4x squared sine of x squared plus 2 cosine of x squared. And we need to plug in 0 for the Taylor polynomial. So f double prime at 0 won't fit here. Won't fit here. It'll fit fine. Minus 4 times 0 squared times a sine of 0 squared plus 2 cosine of 0 squared. Cosine of 0 is 1. 2 times 1 is 2. And all this term is 0. We've got our first non-zero term. No problem. We just keep taking derivatives. And we start thinking, wait a second, what was it you said about not wanting to do all this math? And I'm like, oh, too late. We're into it now. And you're like, oh, but this one's going to be 0. And I'm like, all true, but we need to know what the derivative is so we can take the derivative again to get to the next non-zero one. We got to use the product rule here. At least we only need the chain rule on this one. The derivative of minus 4x squared sine of x squared is the derivative of the first times the second plus the first times the derivative of the second. Derivative of sine is cosine of x squared times 2x. Then we also need the derivative of this term, 2 cosine x squared. So plus the derivative of 2 cosine of something is 2 sine of that thing. Oh, derivative of cosine is negative sine. Times 2x. Because we still got to find f double prime at 0, or f triple prime at 0. So we have to remember the point of doing math classes the point of math class is to avoid math class stuff. This is getting untenable. So right now, we might be thinking, can I just do this? If I want the sine of x squared, can I just replace all the x's with x squareds? And yeah, you can. Sine x squared. The Taylor series for sine of x squared is going to be x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14 over 7 factorial, and so on. We have a procedure for finding a Taylor polynomial that we want to avoid if we can. Now I've just implied that there's another important thing that we can do. We can just replace, if we want to plug into the Taylor series for sine of x, we can even put in a function, just replace all the x's with whatever in the parentheses. That allows us to skip taking all these derivatives, which could get kind of a hassle. Especially notice that we won't get the second non-zero term until we get to the 6th derivative. And look, already at the 3rd derivative, I didn't really want to do it. The 3rd derivative is going to give us a 0. The 4th derivative is going to give us a 0. The 5th derivative is going to get us a 0. But we need all those terms still, so we can look at the 6th derivative and find out that the coefficient is going to be, well, whatever it is. Any questions? If you're worried about where this 2 has gone, remember this is in the 2nd degree term, or the 2nd derivative term, and there's a 2 factorial underneath it, and so they're canceling out, and that's why we don't see a coefficient of 2 in front of the x squared. The same thing happens with all the ones in the middle, or like the 6th degree one. So our current project is to find Taylor series of functions. The next one on the list, that if you want to get a jump on things, is to look at for the binomial series. So where f of x is 1 plus x to the p. This is our series for tomorrow. If you want to get a jump on it, start taking derivatives of the binomial series. And then we'll write down the Taylor series for the binomial series, and we'll practice a little bit with that. This is also known as the starving student series, because starving students binomial. All right, that's going to do it for today. I will see y'all on tomorrow. Find the Taylor series for the binomial series. Everybody have a good day, and thanks for playing.